Hi, welcome back everybody. Today I'm going to discuss about some functions that can be applied to vectors or matrices to do some basic data processing. So the vector that we are going to use is we're going to make a kind of a signal or a spectrum by using mathematical functions such as the Gaussian function on a vector, and then we'll do different operations on that vector to see how we can retrieve information on the vectors. Any spectral data is usually composed of two vectors or more. One is the vector that gives the x values, and the other is the vector that gives the y values. It can be, for example, UVB spectroscopy. It could be absorbance. In IR, it could be transmittance. In NMR, it would be signal intensity, and many other techniques basically have data that can be shown in two vectors. So we are going to make our own spectral data for this. So I'm going to save a file called vector functions, and we are going to make our own data. For example, x will go from 0 in 0.1 intervals until 100, and y will be a function. So we'll take 10 times the exponential function of minus x minus x0 squared divided by sx. So we don't currently have values for this, so this will give an error. So we'll say x0 equals 30 and sx equals 10. So now we are going to plot this. And we'll run this. And it should work. We got a peak function. So if we, for example, let's make another, so we'll call this y1, and we'll make another function. I'm just making up values. We'll run it. So now we have two Gaussian functions. We could make a spectrum that's basically the sum y total equals y1 plus y2. And we will basically now plot y total. So now the green trace is the sum of both. So for example, we can do many things on this spectra. one possibility would be to is to take, for example, the max of y1. If we do this function, we'll get a value which is 10. So 10 is the maximum value, which is, as we can see, it is the maximum value of y1. We could also ask for the minimum value of y1, but that will give us, well, one possible answer. You can see that this is exponential minus 212, so this is basically 0. So that's numerical noise in the database, basically 0. It's probably one of the many 0 values that there are in this vector. So if we go to help max, it will tell us how to use this function. It will tell us a lot. So you should always look at the help to see how it works. So for example, we may want to know where the maximum is. So if we do this, W would be okay, it doesn't literally say what W and IW would be, but we can see here that the W is the actual maximum value and IW is actually the index. So if we say Y1 301, the value is 10. And if we want to know to which X value it corresponds to 30, which is basically the center of the Gaussian that we have chosen. So now if we want to do this the same for function y2, we will get w2 equals 5, which was the maximum value. You can see here that we multiplied function y2 by 5, and the index is 401. So basically, if we say x, we are using the same x coordinate for both functions. So basically the value is 40. The x value corresponding to index 401 is 40, which is again what we wrote. So we can actually use this for the detect maximums of function. But if we do max of y total, basically we get this value 10.006, which it happens because when we summed both functions, we obtain a new vector, which is not exactly the same as before. So we are summing two Gaussian functions that have some overlap, and therefore now the maximum has slightly shifted. We can see that the x value is the same, but now the y value is slightly larger because we are summing two functions. So we can use this function to detect the global maximum of the function, but we cannot use max to detect individual functions. So there are individual maxima. So there are other functions that can be used, but I will discuss that in a later video. So for example, we can take the derivative of this. We can say, okay, dy total equals diff. Diff is for difference, it's a finite difference of y total. So now let's make another figure. Dy total and if we try to run this, it will generate an empty figure. the previous figure is still there, and it happens, we can see here there's an error. The error says plot 2BV, so this is probably some kind of internal variable for the plot, but it says vector lengths must match. Why? Because when you take the difference, the derivative of a vector, you have to subtract each element minus the previous one. So that means that you end up having one less point in your derivative vector from what you had on the original vector. So you also need to decrease the, we are going to call this x p for x prime, but I don't know what name to give it, would be x 1 to n minus 1. It's simply that. So now we are going to use this to plot, and now what we obtain is the derivative. It's not exactly the derivative because we have only taken the difference between the y values. So we know from mathematics that the derivative of a function y with respect to its independent variable x can be treated as a finite difference, at least in an approximation. So this would be approximately y I plus 1 minus yi divided by x y plus 1 minus x y. So this is the finite difference approximation to the derivative of a function. Basically, at point y, you could call it at point y, but it actually would be in between. So this new point would be in between the previous points. So what we can do is, to make this more mathematically more correct, we said, okay, dy dx, so we cannot, we are somewhat limited to the names of variable. We cannot put a dash symbol on a name. So dy dx would be diff y total dot divided, because this has to be an element wise operation, and we will take basically diff x. Hopefully this will work. And now the new x, let's call it x new, would be x y end minus 1 plus x 2 to end divided by 2. So I apologize if this is going a little bit fast, so you have to already know what's the definition of the finite difference approximation to a derivative. So what I did here is take the difference between adjacent elements in the y vector and divide it by the difference between adjacent elements in the x vector. This difference in this case will be always the same number because our x values are equidistant. But if you took experimental data, it could be that the x values are not equidistant. So then you would, this expression diff x would be the correct one. You could make a mistake if you assume that the points are equally distributed. And so what I'm doing then is the new x-axis for the derivative would be the average between consecutive points. So what I'm taking is the sum of the first let's say if I have 100 points here, 1000 points, then this would be the first 999 points, and then this would be from the second to the last element, and I'm averaging them. So now what I will plot here is x new, and I'm going to plot dx dy. So hopefully everything will work. Nope. Dy dx. So now we get the derivative. If you see the derivative here, the values are reasonable. The derivative has a value around below is around 2.74 maximum, and this is more or less in an order of magnitude that would correspond to these values of 10. So we are taking the maximum of the derivative, for example, would correspond to the maximum slope region of the spectrum. So I will simplify this. I will do a new figure, and I'm going to comment this so that I'm commenting so I have not so many plots, and I will add close all so that we don't we close the previous figures. So now you can see I have plot both the function and its derivative on the same plot, and you can see that the maxima of the derivative is coincident to the maximum slope region, what would be the inflection point of the Gaussian. Then the minimum would correspond, which is a negative value, corresponds to the other inflection point in the Gaussian. And the same we have for both Gaussians. So we can see that it's very, very easy to take the derivative of a function numerically in programs such as Octave. So in the same way we can do integration, but for this we are going to use a function called cumsum, which is cumulative summation. So this will not give us directly the integral, but it will give us something which is proportional to the integral. Let's see if this works. So you can see here that we have actually obtained something which is proportional to the integral, but it's actually the scale is too large, because the integral is a summation that's multiplied by the differential in x. So cumsum doesn't give us directly the integral, but something proportional. So we have to multiply this by the x vector. So it's again element-wise operation. So this should give us sorry, we do not multiply by the x vector. It's the differential of x. So this should be x, and this will probably not work because the numbers of elements will be slightly different. So what we are going to, so I will show you how it doesn't work. Non-conformant arguments, operator 1, which would be the cumsum, has 1001 elements, and operator 2 has 1000 elements. So this won't work. So what we are going to do is just the simplest version is 1 to n minus 1. So now this should work. Vector length. So x, probably we have to use x new because I use the dimensions would be the dimensions of the diff of x, and the diff of x has one less element, so the proper value would be x new. And now we can see that the integral is actually reasonable. So for example, if you had an NMR data, you could definitely use this to programmatically integrate your peaks. Of course, you would have to do a lot of pre-processing, like baseline subtraction. You would have to do this numerical integration over a certain segment in the x values, not the whole spectrum. But in principle, these are kind of the tools that you can use for processing many types of real-life spectra or other types of data. It can be anything that can be expressed like vectors or matrices. You can also do, if you operate these functions on matrices, there are the different operators have different rules. Basically, they will retrieve, for example, the maxima or the difference among along columns of a matrix, for example. Or you can choose if you want the maxima or the difference or the integrals along rows or along columns. So there are more options if you work with two-dimensional data or higher dimensional data. So we have seen now 3 functions or 4 functions: max, min, diff, and cumsum, which are I think are useful for doing calculus on data. There are many other functions. We will see in future videos how to actually code some of these functions ourselves using for loops. But in the case of Octave, it is better to, also in any kind of interpreted or high-level language, if you already have a built-in function that does something, it's usually better to use that built-in functions and not try to code it yourself explicitly. So I hope this has been useful. Please, if you find this useful, like and subscribe, and see you on the next time.